So right now we're gonna do a quick revision of the problem set. So this is the programming part. And this is the Julia code. The first part that I basically told you to try to install are the packages that you need. These data frames and the CSV linear algebra are the main ones. These other ones will be useful for later, but let's leave that there. So the first part is just calling up the directory. So if you open using Atom, this part will basically find automatically the folder that you downloaded your folder, the replication AK. So I just leave it at the downloads. So this part should be automatic. Else you will have to have changed it so to find the folders where the data is. Okay. Now the first thing is that we're gonna set up the parameters of this experiment. So there are 154 students or subjects, 50 time periods, and then 3 goods. When I import this data using this command CSV read, the original data is in a CSV file, and basically this is the data, right? So we have observations for different individuals. They have an individual code versus individual one is 102, 108. That's a code is assigned by the experimenter. And then we have 50 observations, right? And then we observe basically the bundle that he chose for X, Y, and Z. And then we basically have the rest of information, starting also where the prices cut the axis. So which is XA, YA, and ZA. Using those axes, we can then compute the slopes, okay? Which is the price. So this part, I'm just going to import it. And then I'm going to use some code from data frames that allows me to break down the data set into individual data sets. I need, for each individual, I need consumption and prices, right? That's what I need to test guard. So this one here, this command will do that. So basically it's going to create, by means of the ID variable, which is the individual identifier, is going to create individual data sets. So as you can see here, we have now a collection of data sets, each of them being one of the individuals, okay? So we can then evaluate it and obtain now an array. So I'm filling this with zeros. This one has as row, so this is a three-dimensional array. So this has 3 dimensions, because the first dimension is individuals, and second dimension is time period, and third dimension is number of goods. And the same I do for CDE, so which is the consumption variable. And here I'm just filling the data. So row is equal to this DOM node, which is this collection of data frames. And so here I'm just filling it with the different observations from 1 to n, and then all the time periods. And basically, these are the locations from the different prices and consumption, okay? So with that in hand, right, what I'm going to do is I'm going to create the individual price and consumption that I'm going to fill. So what are the size of these vectors? Well, is a 50 rows times 3, because we have 3 goods, right? So each price for each time trial is a vector 3 dimensions, and the same for quantities. So this is, for instance, for individual 1. So these are basically the prices that this individual faces, and these are the quantities that this individual chooses, okay? Individual 1, and then I can change it for individual 2 and so on. First, if I change it to 2, I'm going to get new values. So this is the data set of individual 2 and so on. So the main thing is that I want to test guard. Okay, how do I test guard? Well, first of all, I need to create a matrix of reveal preferences, right? So this matrix is going to be 0 ones, and it's going to be a 1 whenever PT times the quantity at trial T is greater than or equal than PT, the price at trial T, times QS, the quantity at trial S. And when that happens, the entry TS will have a 1. If it doesn't happen, so if XT is not really preferred to XS, then it's a 0. So this is the direct reveal preference relation. And this function is going to take as inputs prices and consumption, and it's going to give me a matrix of size T times T, 50 times 50 in this case, with all the information about direct reveal preferences, okay? So that's a function. And then the key part is this. So how do I test GARP? So if I will to test work, the weak axiom, then I don't need to do anything else, right? I just need to use the RD preference and try to see if there is a cycle of size 2, okay? But because I need to test GARP, I need to take the transitive closure, right? So I need to take the indirect preference relation. How do I do the indirect preference relation? Well, this is basically an algorithm that allows you to do that, okay? So now, what is the size of this M matrix? That we're going to feed it is basically the reveal preference relation matrix. So it's going to be 50 and 0. And what I'm going to do is basically go and fill in the indirect preference revelations. I'm going to fill it with ones. For instance, if I is better than K and K is better than J, then it has to be that I is better than J. Okay? Do you see? So this simple algorithm, what it's doing is creating this transitive closure, right? So it goes over the direct preference relation and it observes that, for instance, X1 is reveal preferred directly to X2, and X2 is reveal preferred directly to X3. Then it goes in the matrix and now fills in the 1 3 with a 1, right? So because now 1 is indirectly reveal preferred to 3. Okay, and so when it does that, then it uses this information again whenever you're checking the rest. Now, turns out that this algorithm creates the transitive closure, so it's not obvious that it does, but you know, this is a proof for computer scientists, so we just use it. So in general, so the transitive closure is the difficult part to do. So this is the matrix that does it, and then testing GARP is easy. Basically, we create GARP matrix, which is going to have the results. It's 50 by 50 matrix of zeros. Then I create a matrix M, which is the transitive closure of the reveal preference, direct reveal preference relation that takes as inputs prices and quantities. And then I'm going to go and check for all entries in this matrix. I'm going to basically check the indirect preference relation matrix M. And I check that if T is really preferred to S, XT is really preferred to XS, and there is also this flip of the preferences, right? So PS, QS is strictly greater than PS, QT. So that means that now in direct reveal preferences, QS is better than QT. So at the same time, you have that XT is better than XS, and at the same time, you have that XS is strictly better than XT. So that's, of course, a cycle. And then I fill these metrics with a violation. So the observation T and S have a violation of basically GARP. Do you understand this part? So this is just checking the indirect preference relation matrix and then checking whether in the data it is the case that there is also a direct revelation of QS versus QT, right? So if that happens, it's a cycle, and then it's a violation of GARP. If a violation of GARP happens, then I record a 1. And then I take the maximum of this matrix. So whenever there is 1 violation, I'm done, right? So this is no longer rational. So my test of GARP is going to run over individuals from 1 to 153. And then it's going to be basically 1 or 0. So if it fails, GARP is 1. If it satisfies, GARP is 0. And then, of course, the rate of violations of GARP is 1 minus this average of violations, right? Which in fact is 12% 98%, 12.98%. Okay, so I was checking your submissions. So yeah, so the people that didn't do this problem said, well, you are a bit of a disadvantage for the midterm, right? So try to check out this code and try to make it run. Try to understand what's going on. In general, GARP, this is the main thing you were trying to do, right? This is rationality, so we have to understand it, and a way to understand it is try to code it. Okay, so yeah, I think some of you did a great work. I saw the code also with the Afriel index and so on, so that's good. And now I'm going to go to the, so any question here, and then I'm going to go to my proposed solution of this zero price problem. That's not the one unique solution, but it's the way I solve it, right? So does anyone has a question?
So for example, in the assignment that was given, so based on the code that you gave us, we were supposed to basically change the individual part. That was the main.
You were supposed to do the Afriel index, right? So in particular here, I can define basically E equal to E, right? The E matrix. And then here I will add this number E here, right? So this is the alpha. I'm just going to use E now. So now this is a new matrix, right? The RDE matrix, which is testing for the value E. So when E is equal to 1, it's back to GARP. If E is equal to 0, then everything passes, right? And then I'm filling this thing. Then the tick closure is the same object as before. It doesn't change. And then, of course, I will do the GARP OKE, which the APRED index, add here this E number, right? This matrix, of course, now this is called RDE matrix. And here, of course, I have to modify also multiplying it by E. And that's it, right? So I get my GARP matrix, and then the results are the same. Instead of having the GARP OK here, I'll have the GARP E, and then I'll have to specify here the E value, right? For instance, let's say 0.90. And then this will be the test GARP for, I actually can do it a function, right? So equal to E, and then I can run, for instance, a linear search over E to see which is the higher value that works for an individual, right? So this part, of course, I also send you a code from MATLAB that you can do, which is better than this, but you can also do a strong search and see which is the highest value of E that is compatible with GARP for an individual, right? Yeah, so that was basically the exercise. It was very simple. Yeah, I saw that almost how you submitted, so I don't know. So then, I know these are hard times and everything, but be mindful. So there is no one class that is more important than the other. So if you fail one class in the core exam, you fail everything, right? So this year, this class is very different from previous years. So if someone told you, focus on this other class because it's going to be a little bit easier, that's not good advice. I'm just, telling you that a little bit the trick here is try to allocate time in a way that you are able to cover most of the things. So if I'm sending you this, is because obviously you have to do it again. So understand this is important, okay? So yeah, so I think one of you did really good job. So Brice did actually a really good job. So he plotted the APRED index and so on. So that's really cool. So yeah, I will ask him if he wants to share his code so you can see the full solution. But yeah, I mean, there was not a single way to do it. It was actually a very easy task. So this APRED index is one of the simplest things you can do. And I did it right now, right, in a minute. Okay, so now I'm going to go over the attention problem, the zero price. So let me share it now again, the other screen. Okay, can you see it?
Yes.
Okay, so here Uh, before continuing, so I want you to ask one of you, so to give this part of the work. So who wants to give their own solution before I go through mine? So I saw the submissions. All of them look okay. So yeah, any of the people that submitted, they have, I think, okay solutions, so you can share it. Don't think they're wrong, actually. I think you did a good job. So for instance, Tyson, I think I remember that you did a solution using price ratios.
I didn't think you would pick mine. Yeah.
Yeah,
Price ratios.
so tell me what was a little bit, tell us, I mean, if you want to share as well the screen, but you can also tell us verbally, whatever you choose, right?
Oh,
So
okay.
let's just give a little bit of background so everyone's on the same page, right? So you
Sure.
remember this is the zero price effect, right?
Right.
We have this experiment where we observe these Hershey keys and this Lindt truffle, and these guys, they are really good to write this this story. They make it really fun, entertaining. So as you have this really great high quality chocolate Lindt versus the Hershey, which is average chocolate. And then you have treatment and control. For the treatment, you basically decrease the price 1 cent to each of these two goods, and keeping the difference of prices the same. And then you see a huge change just because you went from 1 cent to zero price, right? And then the people basically switch to Hershey cheese, Hershey keys, more in bigger proportion, even when the difference in prices remains the same. So, summarizing the experiment, you can say that in whenever the price is 15 cents and 1 cent, then people choose A over B, right? And then when you decrease the price to 14 for the Lindt truffle and 0 to the Hershey keys, then people choose B over A, right? So that's the context. So now you can explain with rationality. That was the summary problem set. Now, Tyson, what was your solution?
Oh, so I basically said, if I remember correctly, so the utility, so normally you just compare it's more, think about like a ratio versus the utility over the price.
Mm-hmm.
So it's more of a relative utility versus the cost. But when the price becomes zero, then normally in the mathematical sense that would be undefined. You can divide zero by anything, but in terms of at least the decision making process, we can just say that if we divide by zero, then we can just assign a certain rule. And I don't remember what I said exactly. Oh, it becomes basically infinite. So 1 divided by 0 is infinite. So the 0 is always better. If you divide by 0, it's always better. And that was the basic logic that I thought of. I wasn't sure if that was a good answer.
Okay. Yeah, so great, Tyson. So then a little bit remember that the way what he's changing from the original model, right, is the following. So remember that I was defining utility in a parametric way, right? So this is equal to G, which is the benefit, right? Minus price, which is the cost, right? I'm making these calls basically linear. So this is the assumption on which this, following this book, you cannot be rational, right? But a little bit the question, and I think Tyson got it correctly, is that why is it the case that it should be cost minus price, right? Maybe it's benefit divided by price, right? So the price actually kind of makes it affects this utility in inverse multiplicative way. So the question is a little bit, utilities, they are very non-parametric so far. We have studied just models that are very abstract. When we're trying to model something, then there are many ways prices can enter. So in particular here, we have a budget, but price is only a characteristic. So the fact that I'm subtracting from it is a particular way to model, right? It's an additive way of entering prices. And also, so then Tyson, is in his right, to define it differently by making it inverse multiplicative. And it turns out that this gives you, at least explains a little bit the fact that when it goes to zero, then it goes, to infinity, right? And then, you have this kind of jump. Now, of course, that particular, there is some issue. So that's what I want you to understand, right? So you are basically satisfying the task of the problem set because you're explaining the fact that when you can have with your model people choosing A over V in the first one and then flipping. to the Hershey cheese, right? So B over A. Now, the problem is that in the experiment, right, we have some people switch, not everyone. So according to Tyson, then everyone will be thinking free is always better, right? So you don't have, so it destroys the other information. So if you want to think about kind of out of sample analysis or trying to explain the whole population, it wouldn't be the best model. So usually models that have infinity are a bit hard to work with, right? So even if he gets the idea that maybe, by creating this discontinuity, something can be done, I guess it's not a complete solution. So for instance, you cannot really extend it to new cases. So yeah, I mean, so he was able to fit somehow the in-sample information, right? But it's hard to extend it. Okay. So another solution that I like also was by Brice. Can you hear me, Brice? Brice, can you hear me? I can hear you very low volume. I cannot hear you very well. Well, in any case, so I will try to summarize what you did, Brice.
Hello?
Okay, can you hear me?
Yes.
Yeah, so can you tell us your solution, please?
Yeah, my solution was a kind of like we define like an inattention parameter, which is between 0 and 1, and suppose that the default the subjective price equal to m times the actual price plus 1 minus m times the default price.
Mm-hmm.
And the actual price, when it equals to 0, then for people that have an attention equal to 1, they will like buy free, I mean, product good that the price is 0.
Mm-hmm.
Because in that case, the subject the subjective price equal to the actual price, which is 0.
Okay. Yeah, I think it works. I'm gonna check it with more care. Let me tell you my solution, and then I'm gonna tell you why I did it the way I did it, and then I'm gonna comment more general about the other solutions. So my model is also a model of inattention, right? Instead of having this additive inattention like in our notes and as Brice did, I'm going to use this multiplicative inattention, right? Like Cobb Douglas. So in particular, inattention, if you go to this behavioral inattention handbook by Xavier Gavex that I sent you, he also started this version, right, with the multiplicative, the log additive. So if you apply logarithms, then actually individuals may be thinking changes in prices instead, right? So kind of processing the changes in prices instead of level prices. So this is, if you apply a logarithm, this will become linear, right? So this is kind of the log linear version of inattention. So here you have the psychological price for J, being J, the truffle or the Hershey. And then you have the true price 11, to the power of M, the attention parameter, times P default, right? 1 minus M. So here, I'm not assuming there is timing because in the experiment we have treatment and control. So actually the subjects that face the 0 price and the subjects that face the 1 cent price, they are different, right? So it's not a sequential exercise. So there is no panel. So I'm just going to fix the default price to 1. And I have the following experiment, right? So I have two observations. So first that these guys choose A over B. Okay, so according to this specification, if this becomes 1, then I only have price to the M, right? So I have GA minus 15M greater than equal than GB, which is the benefit, the gross benefit of the Hershey kiss minus the price, 1 cent to the power of M. And then for the second experiment, I want to fit the fact that now they flip. So they pick now V over A. So the inequality is now reversed, okay? So here I have G of A, the gross benefit of the limb truffle, minus the price of the limb truffle to the power of M, the attention parameter, strictly less than GB, 0 to the power of M. So I'm going to avoid the non-defined object. I'm going to assume M is strictly greater than 0, right? So I don't have 0 to the power of 0. But turns out that if I put together these inequalities, right? So they become this triple inequality. And basically, I want to figure out whether this gives me some sort of contradiction or not. And then I'm going to find a particular numbers of GA and GB that explain this data, right? So in particular, this has to be above this, as you can see. So GA is the same, it kills each other. So now I have that minus 15 plus 1 is strictly greater than minus 14. And then, of course, I apply a minus and flip the inequality. And I have this equation, which is a power equation, okay? So now, does this equation has a solution? So is there any m between 0 and 1 open that satisfies this equation? The answer is yes. So in fact, any m in the open interval 0, 1 works. Okay, I don't need that level of generality, but I want you to notice two things. So let m be equal to 1. Okay, if m is equal to 1, what happens? I get a contradiction, right? So 1 cannot be, right? So in the limit, this inequality breaks. This is the rational limit where, of course, if I pick a over v in the first trial, then I have to pick a over v in the second, right? This is the original model when m is equal to 1. So when m is equal to 1, this breaks. But for any other m in the 0, 1 open interval, it works. I'm going to show you by means of one example. That's the only thing I need. So m is equal to 1/2. So say half attention. Then I verify that for these numbers, g equal to 3.3 and gb is equal to 0. Of course, I use a software to find these numbers easily. And then turns out that using these numbers, you can easily verify these three inequalities. And then I have that in the first experiment, A is peak over B. And then in the second experiment, B is peak over A. Okay? So this is a very simple solution. It's not the only numbers that can work, but certainly they work. And you know, this model is interesting because you can calibrate the different G's and the different M's for different individuals, right? And try to, you know, there are many ranges of parameters for which you still explain this data. And of course, as M goes to 1, you go back to the rational model, which is always good. Yeah, so that's an easy model. And again, so now let's think about why I'm using this model, right? So my original idea is that I want, so of course, what makes the zero price effect impossible is this linearity on prices, right? So basically, the difference on prices remains the same when I move 1 cent. So in that sense, if you pick A over B, you should also pick A over B in the second case. So by adding this nonlinearity on the price, you can easily fit more behavior, right? Obviously, in this case, it's behavioral justified because again, these guys are focusing on the price changes because this is log linear. As I said, if you apply the log here, you're just checking how much it changes with respect to the default price, which is 1. So in terms of changes in relative prices. So now, of course, it's gonna look for you higher a price from 0 to 1 than a price change from 14 to 15, right? So this flips the perception of how much you're paying, and now 0 becomes more saving. So this exponential inattention technology works for the zero price effect, and basically that's the job. Okay. So now, how do you know if your model is good or not? So first of all, we have some experimental data, and we know the original model doesn't do the work. Okay, so it's obvious that we need a new model. Okay, so we do the new model. So how do we know our model is good? Well, the key idea is that then you have to make some predictions that are out of sample, right? So you say, okay, now imagine that I now have a third experiment. I haven't run it yet. So it's going to be 16 cents versus 2 cents, the Lindt truffle versus the Hershey Kiss. So then what will be the prediction? Okay. So then you go to my model, right? I use the calibrated M and the calibrated G's. I make my prediction. And now I go to the data and see what happens, right? So basically that's the way I can see my model is good or not. So try to validate it with the parameters I did in sample, out of sample, right? So what I'm doing now, of course, is a toy example. It's more about trying you to play with these things to be able to fit data. So it's almost a calibration exercise. But in real life, basically, that's what you're doing, right? So you run here, instead of this simple calibration, you run an econometric estimation. Yeah, so again, so the way you are able to fit this experiment is basically, there are multiple ways to do it, right? But what I was looking for is basically that you're able to explain the particular stylized fact. So you have to have numbers in your model, certain calibration of your parameters that will give me the main observation of the experiment. First, in the 15 cents versus 1 cent, individuals pick A over B, right? So that means the length truffle over the Hershey Kiss. And when the prices go to 14.0, then these individuals will flip. So your model will have numbers under which this happens, right? If you do that, you calibrate the model to do that, then you have satisfied the model, right? And then, of course, in this particular level of the question, I haven't asked you to derive, implications for the model out of sample, right? So I haven't asked you to understand the model more deeply. I just asked you some model that works, okay? Yeah, so for the people that submitted, I'm going to try to give you feedback on this. Yeah, so for the others, try to see what I did and try to understand. Yeah, so now we're going to go to any questions here? No questions? Okay. So I'm going to go to the notes. Okay, just 1 second. Okay, so back to the expected utility part. Remember this part of I went a little bit fast. I want to go a little bit slower today, just to fix ideas. So a part that we concluded, the expected utility study, was the revealed preference analysis of this. So I want to test the non-parametric test of whether behavior of an individual is compatible with expected utility. So I'm not going to study the full general model of expected utility, but I'm going to study this special version where you have risk-averse agents. So we know risk aversion means the utility is concave, okay? So I'm going to try to get from this problem some sort of Alfred inequalities. That's my objective. So consider the problem of maximizing a utility subject, expected utility in this case, subject to a budget. So this is a portfolio choice. So you have states of the world in capital S, and you're maximizing basically the choices of these ROW securities, which are going to be contracts that pay you an amount of money in each state of the world S. So in particular, X sub S is the money you get in a state of the S, a state of the world S. So for instance, if you have a state of the world shiny and rainy, you receive $10 if it's rainy, $0 if it's shiny. This would come here in the X sub rainy, sub shiny. Okay, 0 and 10 is a vector of 2 dimensions. So X is basically of size RS. Okay, so here let's put it the cardinality. And then here I'm allowing that you can have negative and positive quantities. You can be short or long. So now the budget is going to be such that you pay these prices for these contracts. So for instance, if you want to buy this insurance that pay you $10 when it's rainy, then you have to pay a prime. And this prime is called PS. So this is the price of the rainy state and price of the shiny state, okay? And then they have to be equal to income. And so first thing that I notice is that this U, I'm going to let it be constant across the states, okay? So it's not changing across states. So when I'm trying to take first order conditions then, with respect to XS, turns out that I have the following simple structure. So it's pi s, which is the probability of that state. The partial, in this case, not partial, just the derivative, the marginal utility of xs is equal to the Lagrangian lambda times ps, okay? And this happens for all states of the world. And now imagine I have a data set of ROW securities and prices. And I also know, happen to know the probabilities of each state of the world, okay? This is important. Then I'm going to say that we have a data set, OT is rationalized by a risk-averse expected utility function if there is a continuous concave increase in utility function such that the expected utility of the observed portfolio choice, XT, super T, is greater than equal than the expected utility of any other Y portfolio that is available in this budget, okay? So this is the same notion of rationality, but now I'm replacing the general utility by the expected utility. Got it? That's the only change I'm making. Now, I have this kind of special case of the Afriat's theorem that tells me a simple non-parametric test, right? So you have OT is rationalized by a risk-averse expected utility function. This is equivalent to the following statement. If there are, basically, there are numbers V sub S super T. So that means these numbers change by state of the world, rainy and shiny, and by observation. So in our experiment, how many observations do we have? 50, right? So in this case, you have 50 vitas per state, okay? So in our experiment that we did for 3 goods, it would be S is the cardinality is size 3. So it will be 3 times 50, 150 vitas, okay? And now I have the following properties. First, if xt, so that means the consumption you get in a state S in trial T is greater than equal than the consumption of another good S prime in another trial, say trial 30. Then it has to be that these betas, which are the marginal utilities, have the reverse, because the marginal utility here is decreasing marginal utility. So it has to be on the other direction. And then we have basically the first order conditions have to hold. So that means that for any 2 states of the world, for any trial, it has to be that across the states, pi s beta s super T divided by PTS is equal to the probability of the other state, S prime, the marginal utility of the other state, evaluated at the other state, so beta super T S prime, divided by the price of the other state in that particular trial. And turns out that if you do that, then that's a complete test of this model, okay? So necessity is always easy to check. It's just by first order conditions. I noticed that if I take first order conditions for each state, I get this object that I already told you. And I have that per trial, I have this observation here. Now I replace the values beta super TS by the marginal utility of X evaluated at XT super XS super T. And this gives me the first order conditions. And then, of course, the others comes from the fact that U is concave and increasing. Now, sufficiency, I'm not going to prove it in this class because it's a little bit beyond the scope. It requires an integration argument, but it's not that hard, but it needs some topics that I don't want to do here mathematically. So in other words, what I'm missing from the proof is that I show that the data set satisfies these conditions, then I can build a utility function U. So the way it's done is basically I use these betas that are values of the marginal utility. And then I interpolate a function across these points. With this interpolation, I obtain basically the marginal utility, okay? And then using the marginal utility, I integrate it back and obtain a utility, right? And then basically this will be the utility, the Bernoulli utility that maximize these preferences, okay? This data. So that's basically the work. I'm not doing it because I have to do 2 steps that we haven't done properly here, which is this interpolation step and this integration step in a more general sense, okay? So I'm going to tell you a quick thing. So right now, using this theorem, you could go in principle and try to check this in Julia for a data set I give you, right? So there is this experiment where we have only two goods, and we have the probabilities. So this is in the experiment, so probability of each state of the world. And then in principle, you can test whether these guys are expected utility with risk aversion or not, right? So how will you do it? Basically, you have to check this system of equalities, okay? So this is something that basically is a finite system of inequalities that you will be able to check whether they're true or not, okay? So what is the problem telling you? So what is the data here? You have prices, right? You have consumption here, XT, XS, and you have these beta numbers. So you're looking for betas that satisfy these first order conditions, and then such that satisfy these inequalities, right? So it's a system of here equalities and here of inequalities, and then together, right, they will give you the basically a system of inequalities that you will have a solution even only if your model comes from maximizing a expected utility with risk aversion. If there is no solution, then clearly you cannot be generated by expected utility. So the cool thing about this test, again, is that we don't have to specify the parameters in the U, right? So we haven't talked about the CR array, the CARA. Basically, it's for any utility as long as it's concave, okay? So that's a reveal preference test. Any question here?
Could you just explain that one more time? So you're saying to show in theorem 16 to show part I is true, so we can go into Julia and test a data set that you give us. For example, we test the second condition. Is that what you're saying?
Yeah, so let's say this, for instance, I give you, I tell you, go to your data set, the experimental data set I provided, right? And then test whether the data set comes from maximizing an expected utility that is risk averse. What would you do, right? So here you are given a test, right? So these conditions 1 and 2 depend only on observables. So depends on quantities of each trial, right? And each state of the world. So how many S do you have? So 1 to 3, right? 3 goods. And how many time periods do you have? Trials, you have 50, okay? So you're looking basically for 150 betas that satisfy these inequalities here, condition 1, and these equalities here. You have also the probabilities of each state of the world. And now basically this data is provided to you. This is the documentation of the experiment, so the probability of each state. And now using this, you can now obtain basically a solution or your program will tell you there is no solution possible, right? If that happens, now you can just say, so this test is rejected, so there is no solution, and I'm done, okay? So this is even only if, so if there is no solution to the system of equations, inequalities, you cannot have any Bernoulli utility that will generate this data through expected utility maximization, okay? So it's very general in that sense. So this is in that sense, is a reveal preference test. It's a non-parametric test of whether data can be generated by expected utility maximizing.
Okay, thank you.
So again, this experimental evidence I told you tells you that expected utility is not great. But one important thing I want you to see is that if I start dropping some observations, as Tyson said in previous classes, so what happens if you just have one violations of the model? So let's start dropping observations such that I try to have still passing the model. And for instance, I can see that rationality quickly grows up. So in the first part, almost nobody is passing. This is in the symmetric treatment only. Like this is that's why it's only 47 individuals. So you have here 26%, and as I drop 3 observations, I go to 68% of individuals passing rationality. But if I check expected utility, I'm going to see that only 21% pass, right? And if I check expected utility with concavity, I only have 4%. Okay. So now the question for you guys is, okay, so same question as before. So is it because this model is really bad, or is it because of the experiment? So same things applies as before. There may be measurement error. So people have to check that. They haven't done it. So that's an open question. So what happens if you add measurement error? Will expected utility do better or not? Expected utility is a very simple model, very linear. I don't think it captures how people think about risk in a good way. So I am not surprised that this model looks really bad in data. Again, most people right now don't seem to mind. And then people keep using expected utility, right? And then they keep using it again because it's so simple and nice, right? It's linear. That's why they use it. Things that are linear are the simplest possible model, and therefore it's just tractable. So models that are linear are easy to plug in into more complex models, right? So for instance, you can have a very complex game theory model, a model of auctions, right? Like the Nobel Prize winners, a model of finance, a model of general equilibrium with a lot of complexities. So, there was in previous times, there was a lot of premium to do things analytically, tractably. So having expected utility was almost a must. You must do it because else you cannot have any closed form solution, tractable result. But the model is really bad. So that kind of carries out to any application of the model. So a little bit, what is the state of the art now is trying to modify this model in order to capture more features of the data, right? So again, what I want you to realize is that expected utility is very small, is a very small subset of the rationality model, right? So the fact that expected utility fails, it doesn't mean that rationality fails, right? So, but a little people get confused, and especially in behavioral econ, sometimes they equate the two, right? And it's not the case. So, I don't think it's surprising that expected utility fails, but it's harder to fail rationality. But yeah, so a little bit the question is why people fail expected utility? Well, as you can see, maybe it's just because they don't have these linear attitudes towards states and basically this kind of substitution patterns. So yeah, so there are many things to do there. So modeling risk is still an open question. The main competitors are these probability weighting models that you are working on the problem set, which are actually from Cannon and Tversky, rank dependent models, and also what is called the loss aversion models that deal with the Bernoulli. We don't have time to do all of that. Maybe they will appear in some problem set and so on. But behavioral econ has really dig into these extensions of expected utility, but I don't think there exists a sole winner who will replace expected utility. So this is kind of an interesting part of econ, where things are not completely set. Okay, so I'm going to finish with an important thing, which is measuring risk aversion in the laboratory. Okay, so can you see this this table? Let me make it a little bit bigger. You also have it in your notes. Okay. So, okay. So right now we study basically the model of expected utility and almost non-parametrically. And now we want to study a simple way to do something with this model, right? And one of the main things people do with these models is try to compute risk aversion. So if you become an applied economist, as most of you will, because that's the trend now, so most of you will be applied guys. One of the main things you have to control when dealing with your models of behavior is how risk averse people are. So imagine, for instance, a simple problem of human capital, right? So you are thinking of how people choose different specializations, right? Why some people become mathematicians and why other people become English majors, right? And majors. So why? So of course there is going to be some kind of rational decision making, the utility of getting that particular thing in the short term versus the long term, but also how risky it is to go there. So a lot of people don't like to risk to get low grades, for instance, right? So that's one of the main reasons some people don't go into engineering or math, because it's more likely that you get a bad draw, right? So I send you a hard problem trying to prove a theorem. It's not only, it doesn't only matter, it's not a linear function of effort. So if you spend a lot of time studying and reading, it doesn't guarantee that you're going to get a good draw, a good idea to do the problem. Do you get it? So it's more risky. It's riskier, okay? So so when you're trying to model choices and trying to model how people pick science versus English, then you'll have to condition or control for risk aversion. Do you agree? So risk aversion appears everywhere, right? So if you're thinking of modeling crime, so okay, so why do people commit crime versus not committing crime? Well, some people commit crime because they receive a benefit from it, but they also condition on two things. So the probability of being caught, right? And then of course how risk averse they are. So if I actually super risk loving, I don't care if I'm going to be caught, right? If I'm risk averse, then I may actually be very scared, okay? And that of course risk aversion is very important. So you also, it's gonna also affect those choices. So yeah, risk aversion appears everywhere. Now, so you need that value. And now I'm gonna ask you, how do you measure risk aversion? Okay. So now you know about expected utility, right? You study a chapter on it, you read the Mascolel chapter. Now, how do you measure it? So who has an idea? Who read this part of the notes? Or just your own idea? How can you measure risk aversion for an individual?
Give them some choices, right, to choose, and you can model from those choices what sort of risk is taking.
Yeah, of course. So we need generically a choice experiment, right? And then we have to somehow make them reveal to us what is their level of risk aversion. So, but we're particular design. So Hall and Laurie, they created a famous method, which is called a list method, okay? And I'm gonna describe it. It's very easy and very nice. So basically they provide an individual with a sequence of 10 choices, okay? And then these choices are basically binary choices. So either you can pick option A or you can pick option B. So in each trial, there is only option A or option B. Okay, so first column, second column. Now, the key is that I'm going to fix outcomes in lottery A. So there is only two monetary prices, $2 or $1.60. And then in outcome B, I have 3.85 and 10 cents. And the key is basically that I'm going to put probabilities here of each of these states of the world, such that basically the expected outcome of A, expectation, first column, is higher for the first four rows, and then it switches to lower than column B, expectation, for the last six rows. So let's think of the benchmark of a risk-neutral individual. So you have a risk-neutral individual, then this guy has the identity Bernoulli utility. So this guy basically doesn't care about risk in one way or the other, and therefore, what will be the behavior of this guy in this design, given this information? So can Fatima, can you hear me?
Yes.
Yeah. So can you tell me, please, do you understand what is a risk-neutral individual, right? So
Yeah.
the Bernoulli utility is identity. So in this design, what would you expect this individual to choose in the first four rows? Column A or column B? So this is the
Column
key.
A.
Column A, right? Because the risk neutral guy just have the expected value of the random variable is his utility or her utility, right? So therefore, if in the column A, the expected outcome is higher for the first 4 rows, then you will expect the risk neutral guy to pick A 1, 2, 3, 4, and then flip to B from 5 and on, okay? So do you get it? So for the risk neutral individual, we have now a benchmark. So now, if I want to classify guys into risk averse and risk loving guys, then I'll just have to check this threshold. So if you're risk averse, you're gonna switch way before 4, right? So for instance, you may switch at 3, or you may switch at 2, or you may actually go from 1, right? Depending on your intensity of risk aversion. So the quicker you switch, the more risk averse you are. Got it? And then you do the same for the risk loving guys. So they are going to, the risk neutral guys flips at 4. Okay, so at the row 4, they goes to option B. Okay, so now you have now from 5 to 10, if this guy delays the switching and actually switches later, for instance, at 7, 8, 10, 9, this guy will actually be way more risk lover, right? And in particular, if it switches at 10, then it has a very extreme risk loving parameter. So it really likes to take risk. So now, so in this way, we can actually rank them into more risk averse or less risk averse. Do you agree? So for instance, if you switch at 4, you're risk neutral. And then if you switch way before that, you're very risk averse. And then you switch way after that, then you're way, risk lover. Now, the important thing here is that we can actually quantify also risk aversion, give you a number. So how can we do this? Well, we pretty much take a relative risk aversion and think of basically a simple model like the CR array, okay? And then I'm looking under the CR array for the parameters under this model, and I'm going to see what are the predictions of this model. So for this range of parameters of the relative risk aversion, minus 1.71 to 0.95, basically the last choice is going to be still A, right? And we can check basically the proportion of choices, payoffs times 1 and so on. And whenever this guy flips, we know the parameter is in this bracket. So for instance, if we go to the 4th row, then we see that this has minus 14 and 15. So that means that the relative risk aversion is exactly at 0, right? Which is the risk neutral parameter, okay? So at row 4, we have the risk neutral guy. At row 5 is going to be risk lover, so positive numbers. And at row 10, basically you become this guy that is completely likes only risk. And in row 1, you have this very high risk aversion level, okay? Which is minus 1.71, okay? So again, so this is a very simple way to do this design. There are 2 aspects that you have to realize when you do this in real life. First is that you cannot pay them for each row, because then you will create dynamics, right? So you want to understand this problem as if it were static. So because of that, you actually need to pay at random. So the way this is incentivized is that you're gonna pay according to the realization of these lotteries. So you're gonna give them actual tokens, and then tokens exchange rate to money. According, first picking one of these 10 rounds at random, and then I'm going to pay you just for one of the trials, right? So I cannot pay you for each trial because it's gonna cause issues. It's gonna create dynamics and hedging. So yeah. Now, surprisingly, so this Hall and Laurie list design, is one of the most used tools for apply guys. So now, because it's so easy to collect your own data, you can actually run your own survey, right? So your SurveyMonkey Qualtrics data, and then basically collect this data on top of any data set you have and match the risk aversion to the information you have. So yeah, and now, so risk aversion, this is the way you can compute it. And of course, this one here is assuming expected utility. as you can imagine. Now, as you could, so we see that people use it and they power through it. We are now assuming that we have binary choice. If you have just binary choices in lotteries that are very similar, I don't think linearity is that crazy. So you can think almost like a Taylor approximation to the real model. So this Holland lottery is not that crazy, but we're going to see a way to try to reconcile these ideas of rationality with real behavior. And this is something that we're going to do in the next chapter, right? So any questions here for this method to understand lists? We're going to take a break of 5 minutes, but I'm going to take any question right now from this chapter.
I'm pretty confused about this experiment. So option A, say like the row number 1. So that you get at the 1/10th of chance you get $2, and 9 out of 10 you get 1.6.
Yep.
And then the B is, there's a low chance. So the expected value is higher for A, at least in the row number 1, for example.
Yeah, so for column A, the expected value is higher from row 1 to 4.
Right.
And then it changes, okay?
Right. So some people might pick B because it pays, there's a chance of winning 3.85, which is more than $2.
Yeah, the key is that option B has higher variance. So it's always worse in terms of risk, right?
Right.
Yeah. So that's basically the idea. So but remember, you have a risk neutral guy, right?
Mm-hmm.
And then this guy, his or her utility is going to be expected utility. So they're going to pick option A first, right?
Mm-hmm.
And then eventually flips exactly at row 4, okay?
Right.
So then if you're risk averse, you're gonna switch before, right?
Mm-hmm.
And then if you're risk lower, you're gonna switch after, okay?
Okay.
Sorry, it's the other way. So of course, is the given that V is higher risk, you have 6 and 10 is risk averse, right? And the more risk averse, the later you switch. And basically you have these parameters means the same, right? The outcome B is always higher variance. So you only flip to that if actually you like risk on the expectation is really high, right?
Okay. Thank you.
I have a last question for this table. So like once you switch, can you switch back? So for example, you start from A and you switch to B. Are you allowed to switch back to A later?
Okay, that's a great question. So 2 things. So you can design your service such that they cannot switch back. So the moment they switch, you stop already, right? And then you compute the risk aversion. Then that's easy to do in a Qualtrics service because you can program it such that you jump to the next question, right? So in that way, you can never go back. Now, because most of these lists are done by pen and paper in the old times, so that means that actually people could flip back, and they did. But if they do that, that means they are not expected utility maximizers, right?
Okay.
Now, a question for you: why do you think people flip back? What is the reason?
Why people flip back?
Yeah, why do they flip and then they go back?
I'm assuming that they didn't do their calculation right.
Well, maybe it's an error, but also it's just because, another explanation can be that your risk aversion is changing, right?
Okay.
Or another explanation is that you actually like to randomize. So you like to explore options by checking the other alternative just in case, right?
Okay.
So right now, and this is actually a good opening for the next part. So right now we're going to take a break, right? So 5 minutes. Okay. We're back at 2:08. Yeah. But I'm just gonna keep talking. This is more of the class. So the key here is that this is a good opening for the idea of random utility. So the question is these models of utility maximization actually any good? Can we predict individuals in a deterministic way? And you point out something that is, you know, a key defining feature of behavior. So you have these individuals, they go and face this list of choices. They may be jumping around, right? So they flip to the column B and then they flip back. So why do they do it? Because they may make mistakes, because they may be tired. So there is always a component of unpredictability, right? And this is the stochastic component. So in a way, we should expand our theory of utility maximization to random utility, to allow randomness, okay? So this is what we're gonna do next, okay? So see you in 4 minutes.
Okay, thanks.
So we're back. So anyone among you has read Asimov Foundation? So this is a very cool book, right? So it's about it's a crumbling empire, a galactic empire, and then there's this scientist that is a specialist on something called psychohistory that creates a planet of wise people that try to preserve knowledge from the destruction of the empire, right? So it's kind of a galactic version of the Roman Empire and medieval times. But the key idea in something that is really cool about that paper is that this psychohistory is supposed to be a science that is able to predict behavior of the history of these galactic empires of humans way far in the future to a very high degree of precision. So I wanted to ask you, basically, you guys, what do you think about trying to predict behavior? Yeah, this is a science question. So do you think it's possible to predict behavior of humans? So I want you to think carefully about what does it mean to be thinking of utility maximization. It basically means that if I know your utility, right, then I will be able to predict all your choices. And moreover, right, if you have a utility, then every time you face the same prospects or choices, you're going to pick always the same. Okay? So let's bring it to real life, right? So you are choosing your dinner. So you're right, you already settled down in London, so you are using some sort of app, Uber Eats, Skip the Dishes, or whatever you use. And then, 6 p.m. arrives, you start choosing. So during a week, basically, imagine there is no promotions, all prices are very similar. And what that means is basically your choice set is more or less the same in these 3 consecutive days. However, the first day, you order basically something from this restaurant, tahinis, baraka, rice and whatever. Then the other day you order pizza, the other day you order a Subway sandwich, okay? Okay, good. So it's the same choices, but you chose 3 different things. So if we're going back to our model, the models we have studied in the previous chapters, that means basically that you have revealed to me that you like first Barakat over the other alternatives, and then you revealed to me in the second day that you like now the pizza to the other alternatives, and the third day you revealed to me that you like the Subway over the other alternatives. So basically that means your preferences are inconsistent, right? In the sense of work. We're assuming here, simplifying, that prices are more or less the same and so on. But what's going on? In reality, people do that, right? You change your choices a lot. So why? So why is it the case? So
I think one reason is that people's utility for, let's say, for sandwich changes. So let's say the first time I eat sandwich, my utility is 10. And then if I eat it again in the second day, my utility may decrease, right? Because I just consume sandwich in a row, and may in third day it decrease again. So in this case, my utility actually changes. That's why I flip my choice.
yeah, that's a good, interesting idea, right? So for instance, somehow you consume not only the sandwich, but also the memory of it, right? And therefore this influences your future. But at the same time, there is kind of a simple explanation, and is that sometimes you are craving for some food, right? So you wake up and you're craving for ice cream. Why? So I'm just telling you that choice is really hard because humans are really complex, right? So if I try to predict the behavior of any of you, is going to be a super hard thing because there are so many factors that are very difficult to model and understand that will influence your choices, right? So think about cravings. So what does it make you crave? For instance, today something salty, right? And maybe if I were a doctor, I will check your blood and see that you have low levels of potassium, right? But in reality, I'm trying to model this as an economist.
Victor,
So,
it could be such that it's not nothing but preferences. Like you're trying to figure out, like try out every alternatives, right? So you're trying out pizza, sandwich, and stuff because you want to see, what choices you have, like what all alternatives you have.
maybe you don't know the choice yet. Maybe your processes are incomplete, right? That's another reason. Yeah. So the reality is that it's so hard to model individual choice because there are so many factors that we don't take into account, right? So now the question is, so what does it mean? Do we give up? What do we do, right? So again, a little bit the next question should be, what is the objective of econ and even decision theory? So do you think economists should model the individual decision making, or are we focused on something greater, like for instance the behavior of a market, of a conglomerate of people? What do you think, guys? So what is the object of interest for economists?
I have a kind of question related to what you're saying.
Yeah.
Would it be, fair to say that, like, if I have like these choices that I'm making over time, the frequency of the times, like, even though these choices might be contradicting each other, the fact that I choose one option over another more times, like over a certain period of time, revealed to me that, like, in the end I have a higher utility for this type of stuff.
Yeah, that's a good observation, right? So this was Eduardo, right? So Eduardo was saying something interesting, is that maybe I don't need to look at the individual choices, but rather as some sort of aggregate choice, right? So if I take, for instance, the choices in a year of you among food, and I see that conditional on many things to keep more or less things constant, you in average pick more often pizza over sandwiches and over rice dishes, and then that means that you might somehow like more the pizza over the other two, right? But now I'm using the frequency of choice as the object, right? That's a very different object because this is an aggregate object, okay? So now that's pretty cool. But now let's think about the aggregation among individuals, right? Because you know that Amazon makes billions, trillions predicting your behavior, right? So they know what people are going to pick. That's how they are able to predict what goods they have in their warehouses and how to optimize their delivery systems, right? So how can they predict? Are they looking at you as individuals, or what are they looking at?
I think maybe it might have to do with something along the lines of like uh, what's hot right now in today's market, and
Yeah,
maybe
but
like
for whom? That's the key, right? So I think that's the key idea, and that's why I'm going to the psychohistory, right? So I'm gonna read you the axioms of the psychohistory, right? So this idea by this sci-fi science basically says that one cannot foresee the actions of a particular individuals, right? The laws of the statistics as applied to large groups of people could predict the general flow of events. So basically, Asimov is thinking as a physicist, right? He's saying, look, think of a gas, right? So an observer has great difficulty in predicting the motion of a single molecule, right? But if you take basically an aggregate of these molecules, then you can do something, okay? And then basically this guy has these axioms of this sci-fi theory, that the population whose behavior was modeled should be sufficiently large, and the population should remain ignorant about the results of the application of psychohistory. Okay, so there are many factors that influence choice, and you mentioned some of them. But my main question was about what is the unit that is predictable? Okay. So what I'm going to do now is I'm going to introduce a new idea. I'm going to say, look, maybe we shouldn't model the individual level, but we should model the aggregate level. And by that, I mean, maybe we should model, for instance, the market shares or the fraction of people that choose a particular alternative. So think, for instance, that tomorrow I become a part of Uber Eats, right? They hire economists, by the way. And so they want to know, how to optimize the location and timing of their different vehicles in a city. So they need to have an idea of demand of different restaurants. So even if I don't know exactly what any of you will pick for dinner today, I can predict very, to a high degree of confidence, the share of people in London that will like more Baraka to Subway to Papa John's. Okay, do you agree with that statement? So the idea is basically that it's easier to predict aggregates, shares, market shares, for instance, than individual behavior. Okay, but now how do we marry the two ideas? So how do we have still the idea of utility maximization and have now the notion of aggregate behavior in a way that makes sense? So in Mascolel, there is this very lame chapter 4, which is the worst chapter in all Mascolel. And we're not going to do that. So full disclosure, you can read it. It's very short and easy. That gives you a terrible answer. That tells you, look, if you're rational and I take average behavior, then average behavior is no longer rational. So less despair, right? And that also tells you that a representative agents in macro are lame and bad and you shouldn't use it. Okay. Now, given that, okay, we know that, everyone understood that. So chapter 4 is already obsolete. What are people doing now? Okay, so people are doing a stochastic choice. Okay, and this is what we're gonna do now. So I'm gonna share now the screen. Okay, so chapter 15 that I'm gonna move to the after the chapter 7, so it's gonna be the new chapter 8. But so you can go in your notes to chapter 15. This is about discrete choice and logic. So we're going to start with a framework of utility maximization. And I'm going to start adding to it stochasticity and trying to start thinking of aggregate behavior. Okay. So for simplicity, right now, we're going to change to a setup of discrete choice. So there are J alternatives. So for instance, restaurants in London, okay, that are open today at 6 p.m. So this J alternative, say in London is, maybe how many restaurants do you think there is in London? Maybe 20, I don't know. So, and then, we have each of them is an exclusive choice. So if you order from Baraka, you cannot order from Papa John's, right? That's the assumption now. So now each purchase occasion, the consumer divides the income, YI, on at most one alternative on an outside good. So the outside good is going to be, in this particular case, the composite good of all other things that are not ordering food, right? So in particular, it can be, saving money and eating at home. All this composite good is going to be set. And this is the composite price PZ. And then what you want to do is pick the alternative that makes you the happiest possible. So that means you're picking, of course, also the level of savings such that you maximize the utility. So there is this individual utility for each individual I. And now you have here some sets of attributes that characterize the restaurants, right? Like, for instance, their price, how good they are, how many stars do they have in Uber Eats, in Google review, and so on. And then subject to a simple budget where you want to hit some target of expenditure, YI, individual based, your price associated with a good is PJ. This is the price of the dish, average dish at Baraka, for instance. And then here you have basically the interest rate for savings. This PZ is you can set it to 1. So it's not that important, but this is the money basically that remains or is the adjustment variable. And so these X variable are characteristics, right? So we can think of them as being, for instance, the stars in Google review, you know, how spicy, how flavorful, how warm they come and whatever, how fast they are. And now you have here basically a zero option, which is this alternative, the outside alternative that is not eating, not ordering from Uber Eats. And so by playing with this simple condition here, you can now replace Z by Y minus PJ over PZ just by playing with this equality of the budget. And that means I can obtain what is called the indirect utility. So this is the indirect utility of individual I for good J that depends on the alternatives of these goods, Xj, the price of J, the price of the outside option, and the income. And in particular, this is basically in this form because Z doesn't appear anymore, but instead appears the income minus the price. So you know that price is going to affect negatively this utility, and then attributes are going to affect in some unknown way the utility. And then you have the outside good, which is going to be normalized to zero attribute, so staying at home. And then this is the amount you're going to pay. So now, if you consume the J brand, say Barakat, then you're going to get here this max utility according to J. So you can convert this problem into choosing the maximum indirect utility. You're going to pick the one that gives you the highest happiness, of course. So everyone understands this problem. So this is a slight modification of chapter 3. Instead of having consumption bundles, we are choosing here discrete choice, right? So we're choosing just one good, and then the outside good. So the outside good is continuous, and the other is a discrete choice problem. So you're choosing one exclusive good. So if you choose J, you cannot choose J prime. So you cannot choose pizza, right? Now, okay, so we have this model. And now my claim is that if I try to do this for any of you, I'm going to fail, right? It's going to be very hard to model your individual utility and your individual decision. I cannot predict easily today what you're going to pick. I cannot tell you the probability that you're going to pick today Barakat, right? However, if I think at some level of aggregation, maybe I can do something. So now how can I think of the aggregate behavior? So aggregate behavior here is going to be our object of interest is going to be the fraction of people in London that picks Barakat today, right? So everyone's agreed. Everyone understands what's that object, right? So it's basically a market share. Okay. So now we want to model this in a way that allows us to understand the population market share as coming from individual behavior. So the way to do it is to understand basically this individual decision making, right? The indirect utility as being basically the sum of two objects. Here I'm going to eliminate this here. So it's going to be some common utility to everyone that is going to be called the average utility that is the same across every individual and depends on attributes of the different restaurants. So the stars in the Google review, the price of each restaurant, the price of the outside good, and the income of the individual level. And then every variation in behavior across individuals is going to come from something that is a random shock. Okay. So epsilon here is a random variable that is going to affect either increasing the utility of certain good or decreasing it. So in this epsilon, I want you to understand that this epsilon, when I call it random, I'm actually putting everything that I don't understand as a modeler about behavior, right? So for instance, maybe you have a crave for rice, right? So then enters into a positive epsilon. Maybe you really didn't want to taste this particular flavor that you remember from this restaurant. So that's a negative epsilon, right? So maybe today, you have a really bad day, so you want more, more filling food, and that's a, positive epsilon. Maybe you wanted to start a diet today because you saw some advertisement on the TV telling you being, you know, slimmer is healthier, you know, whatever. And then epsilon is negative, okay? So all these things that we cannot know for the individual level now are going to be modeled as a random variable epsilon ij, okay? This is a brand or good specific realization and individual realization. And then we're going to assume something about the distribution. And this is the key part. So to understand the model that I want to tell you basically is that I'm going to try to model the probability of choosing for basically alternative J when prices are P1 to capital PJ and the outside price is PZ, and then you have income Y, okay? What's going to be this probability is going to be the probability of all shocks from epsilon 0, the outside option, and epsilon J, such that the random utility of J is strictly greater than the random utility of J prime for all other alternatives. So when you realize random utility is higher for Barakat than for the pizza and for the subway, then you're going to pick that particular good. But I only can now predict a probability, right? So now this is the part that matches with the psychohistory thing, right? So what is the key assumption that I'm going to do when trying to model market shares, right? Is that this epsilon here, right, is going to be IID, okay? So usually, in order to model a population market share, right, I assume that this epsilon here is distributed IID from some distribution F, right? So what does it mean to be IID? So it means that every random shocks, right, across individuals are first of all independent among the individuals, which may be now a hard assumption to make, but that one is a little bit, you can relax it a bit. But the important thing is that this right now is basically independent and identically distributed, okay? So in a way, we're saying that every one of you, you know, has a common utility that is called the average utility. So everyone has a shared utility. And then every difference in this particular preference for different restaurants comes from this idiosyncratic shock. So this is something that comes from some distribution of preferences that affects you, right? But then if I take some average of it, then of course it's not going to matter much, because if I average this random variable, then I'm gonna get something more predictable. Okay. So right now the class is done, and so you can go. I'm gonna stop the recording. I'm gonna take questions.